Welcome. This is a lesson on graphs, and we'll cover the basic definitions and ways to go through a graph, also known as traversals. It will cover pretty much all the information you need to start solving basic graph problems. And I'll also go over more graph information in other videos, so if you already know this stuff, check out my channel in the description for more advanced resources. And before we start, there's one kind of prerequisite. One of the algorithms covered in this video, namely DFS if you know it, requires a knowledge of recursion. But this algorithm is not actually necessary to know because there's a more powerful one, namely BFS, that doesn't need recursion, but the recursive algorithm is simpler, so you may want to learn it anyway. So you don't really need to know recursion, but if you still want to so you can understand the full lesson, then check out the description for this course's video on it, or if that's not out yet, something else. Now, here's my effective resume in terms of competitive programming. I'm going to do this at the beginning of every video. I have about 3 years of experience in competitive programming, and I reached the rank of International Grandmaster on Code Forces and 7-star on CodeChef. In terms of Google stuff, I've gotten to round 3 on CodeJam twice, and my best rank in Kickstart is 10th, which somehow I also got twice. I also have 1.5 years of experience talking at a screen, just like this, so I've gotten good at explaining this kind of stuff. The point of this resume is not to flex, because there's not really a point in doing that. I just want to say you can trust me. I know what I'm talking about. I'm not going to mislead you or confuse you. This lesson will be accurate, well thought out, and complete. And with that said, let's get into the lesson. But before we start the lesson, let me give you a quick overview on how this is going to be structured. I'm going to start with the fundamental definitions so you can understand exactly what a graph is and also how you can think about representing one in code. We'll do one problem to help you solidify that representation, and then we'll realize that just the definitions aren't really that helpful for solving problems. So after that, we'll cover something that is actually helpful for solving problems, namely 2 methods for going through or traversing a graph. Then we'll do a bunch more problems involving those methods to help you confirm your understanding and tackle some common problems you might encounter involving graphs. That will finish off the lesson, but I'll also refer you to places where you can find more problems if you check out the website in the description. Now let's do some basic definitions. Most of these terms are going to be pretty intuitive, so you shouldn't really think of these as things to memorize, but rather just how to understand these terms in the context of graphs and the context of problems you're doing. And it's going to be a lot of definitions, but you definitely don't have to remember everything, for sure. As you solve some graph problems, these terms will become second nature, they'll become more and more obvious, so you'll get the hang of them over time. And if you really need, you can use this section of the lesson as a quick reference for the common definitions. Now to start off with definitions, let's imagine just a small town. There are some houses and there are some roads between them, as you can see. So the houses can also be nodes, they can also be called nodes or vertices, and there's no real way to actually define what a node is, but they're kind of just points that represent, for example, locations or houses or whatever they mean in the current problem. Usually we just draw them as circles. And the roads can be called edges, and edges are essentially connections between nodes. Usually we draw them as lines between the nodes, representing that 2 nodes have an edge between them. A graph is the town itself. It's a network of nodes and edges. There may even be multiple different towns, meaning that the towns can be disconnected from each other, but they'd all be considered part of the same graph. And I should note, none of these definitions really make sense out of context. It's like trying to define a point or a line in geometry. Like you're trying to attach a definition to it. I can point to a town and say that represents a node, but really what matters is how you use them in problems. So you'll get a better grasp of these definitions when we start doing examples, but right now we need more definitions before we can actually solve anything. So 2 nodes are adjacent if there's an edge between them. So it's pretty similar to what adjacent means normally, like 2 adjacent houses, stuff like that. And 2 nodes are neighbors, which makes more sense in the town example, if they're adjacent to each other. This word is equivalent to being adjacent, but it's used in different contexts, like iterating over all the neighbors of a vertex. And here's some stuff that's hard to classify, so I'll just call them parts of a graph, I guess. I don't know. A path between 2 nodes is a list of adjacent nodes leading from one node to another. Think of it like a physical path, like a trail between houses. Like a path between 2 houses in the town. For example, the green nodes here form a path because adjacent nodes in the list are adjacent in the graph. The red nodes do not form a path because these 2 nodes aren't adjacent to each other. So essentially, you kind of have to be able to walk along the graph by following the path from the starting node to the ending node. And in a path in real life, with the town example, you'd have to walk along it for it to be a valid path. And typically in a path, nodes aren't allowed to be on the path more than once, and neither are edges. Similar to a path, a cycle is a path that starts and ends at the same node. Except for the start and end nodes, nodes are still not allowed to repeat, and neither can edges. So A to B to A, for example, is not a valid cycle because it uses the A to B edge twice. There are other types of paths and cycles where you can repeat, for example, nodes but not edges, like trails, walks, circuits, stuff like that. But it'll be a waste of time to cover all those terms, so I'm just not going to. You can search them up if you need them. And usually a problem is going to define the terms it uses anyway, so you can search them up on the fly, so don't worry about them too much. And two nodes are considered connected if there's at least one valid path between them. This is different from adjacent because two nodes can be indirectly connected through another node or multiple other nodes. Imagine that a virus originates in A and infected every neighboring town and then the neighbors of those neighbors, etc., until it had nowhere left to spread. The nodes that are connected to A are the ones that will receive the virus because they have some path through A. Also note that connectivity is transitive. So if A is connected to C and C is connected to D, then A is also connected to D, which is true in this case. This will be important for the next definition, which will happen right now. A connected component is a group of nodes that are all connected to each other. But that's actually not enough of a definition because A and D themselves are a valid component, but that's kind of weird. We want the whole group of A, C, and D to be the component. So let's add to our definition. Let's say the component also has to be maximal. And that means that if there's some node that would belong in the component, then it has to be in the component. So A and D are not a valid component by themselves because C is connected to A and D, so it can be in the component, so it must be in the component. So essentially the component has to be as large as it possibly can. That way the component exactly represents the nodes that will receive the virus. Nodes can't choose to not receive the virus, and similarly, nodes can't choose to not be in the component. Now all this should be pretty intuitive. It should fit your definition of what a component would be. For example, the red circles here represent the components for this graph. The maximal thing just means that we can't have the weird partial components like A and D, or in this graph H and F, for example, or even A and D in this graph. It's got to be the full thing like the red circles. The edges of the graph can also have some special properties. For example, a graph can be directed or undirected. If a graph is directed, then all of its edges point from one node to another. And it generally means that you can only move in the direction that the edges point in. And paths and cycles in directed graphs work exactly how you would expect them to. You can only take paths and cycles that follow the directions of the edges. So you can't have a path or cycle that goes backwards along an edge. They all have to go forward. In a directed graph, there are a bunch more terms. A node X can reach another node Y if there's a path from X to Y. And this is different from undirected connectivity because it's not necessarily a two-way relationship. For example, in this graph, A can reach B, but B cannot reach A. So in some cases, it can be a one-way relationship. Connectivity actually has the same definition in directed graphs if you think about it, but it has a different term. Two nodes, X and Y, are strongly connected if both of them can reach each other. In this example, A, C, and D are all strongly connected to each other, and B is strongly connected to nothing. And similar to connectivity, we have components for it too. A strongly connected component is a, once again, maximal group of nodes that are all strongly connected to each other. Again, maximal means if a node is able to be in the component, ignore that, then it has to be in the component. So A and D can't just be a component by themselves, C also has to be in it. There's multiple algorithms for finding these components, but that's beyond the scope of this lesson. But you can feel free to check out some other resource for it. And graphs can also be weighted. That means that each edge has a value associated with it. In our town example, the weights could be the lengths of the roads, for example. Then problems can ask for stuff like the shortest distance from one node to another. And there are a lot of algorithms for shortest paths, but those are also beyond the scope of this video, so don't worry about them for now. We'll handle those later. If a graph is unweighted, then it's like all of its weights are 1. And usually for unweighted graphs, we just don't draw the weights because we don't need to. And unweighted graphs are simpler because all the edges can essentially be treated the same. They're all weight 1. So more algorithms would work for them. This will be important later. Here are a couple more properties that some graphs could have. Usually a problem will just give you like this type of graph, for example. A problem could say it gives you a simple graph or a connected graph and you have to do something with it. So if a graph is simple, then there's no duplicate edges and no edges from a node to itself. It means exactly what it is. It's simple. It makes things simpler. It makes algorithms simpler. You have to think of less edge cases on simple graphs. So most problems, to be nice, will give you simple graphs because, again, they get rid of edge cases. But if a graph isn't simple, it doesn't mess up that much anyway. So it's not that important if a graph is simple or not. Sometimes it is, but also sometimes it isn't. If a graph is connected, then it has only one connected component. So every node is connected to every other node. If a graph is complete, then every node is adjacent to every other node. And this graph on the right, for example, is an example of a complete graph size 4. Every edge that can be in the graph is in the graph. And if a graph is acyclic, also known as a forest, then it has no cycles. We'll take a much deeper dive into acyclic graphs in a different video, but just know that a lot of problems are much easier to solve on acyclic graphs. If you've heard of trees, a forest is essentially a bunch of trees together. So yeah, a lot of problems are easier. And now we go back to relevance. Now, it was a lot of definitions that we just went over. Are all of these really going to be useful for problems? And the answer is yes. You will need this knowledge for problems. But no problem is going to use all of these at once. If you ever forget something, you can come back to this lesson or search up the terms you don't know to remember what they are. So you, again, do not have to memorize these, and you should not. Problems tend to define the terms they use anyway, so it really will not be an issue if you don't immediately remember what everything is. And you may also be confused about some things. One being, how can you actually solve problems with this information? For example, I haven't talked about how you can actually find connected components or determine the distance between two nodes. I haven't given you much yet. And that's true. You can't really do much with just the definitions. We needed to do them because it's a fundamental baseline that you need to know, but you can't do much with them yet. So that being said, we will get into the useful stuff very soon, so don't worry. And another thing you can ask is, how do we code graphs? I've given you a bunch of theory, but not like anything concrete. How do you store a graph in code? And that's what I'm going to do next, because we need to. I'll talk about 2 different ways to represent a graph in code of varying usefulness. The first way is a simple form of storage called an adjacency matrix. It's essentially just a 2D array where the array index A, index B is true if there's an edge between A and B, and false otherwise. So for every possible edge, it just stores if that edge exists or not. Note that this also works for directed graphs, except only one of them will be true. Like the array of A and B can be true, but B and A might be false for a directed graph if there's no edge in the other direction. Now think about what this can be useful for. It's easy to check if 2 nodes are adjacent because we can just check if the edge exists in the matrix. But it's also O of V squared in memory, where V is the number of vertices. You usually use V instead of N, and E for edges. So there are some trade-offs. If there are a lot of nodes or vertices, this just is not going to work. It's not that useful, and I personally don't use this that much, but it's worth going over because some problems will give you an adjacency matrix, so you should know what it is. But yeah, let's do something better. The next and infinitely more useful version is called an adjacency list, but actually it's multiple lists, so don't get confused by that. The gist for this is, for each node, you store a list containing all of its neighbors. For this graph, here's what it would look like. For example, B is adjacent to everything, A, C, and D. D is only adjacent to B, and so on. This can be up to O of E, where E is a number of edges, for checking if an edge exists, but it's useful for a lot more things. Its space complexity is O of V plus E, which is much less than O of V squared usually. Or it can be much less than O of V squared. And you can iterate over all neighbors much faster than with an adjacency matrix. So in this case, because the complexity is just the number of neighbors. So I personally use the adjacency list for basically every graph problem, unless like the problem explicitly forces you to use a matrix, but generally that's not going to be the case. Especially also because a lot of problems have a high value of V, for example, V up to 10 to the 5th, where O of V squared is just not going to work, and an adjacency matrix is just not going to work. So I actually can't think of the last time I used an adjacency matrix, but yeah, that just goes to show the list is very useful. And actually the title of this slide should be adjacency list. That's a copy paste error, so that's cool. Yeah, don't do that when you're coding. That's funny. All right, now we'll quickly go over a problem to help you make sure you understand the stuff I just talked about. You're given an undirected, simple graph. Remember, simple, no duplicate edges, no edges from a node to itself. For each node, output the list of its neighbors. So yeah, pause the video and go do that. And if you want a hint for it, just think about the graph representations I just talked about. Should you use an adjacency matrix or list here? If you still don't know, pause, spend some more time thinking. The answer is you should use an adjacency list. This is basically exactly what it's for. This problem is just a stepping stone to make sure you can code the adjacency list correctly, because we're going to need it for later. So go ahead, code it out, report the neighbors, and yeah. In this case, for each edge, x and y, you add x to the list of y's neighbors and y to the list of x's neighbors. This is how you would convert a graph from input to an adjacency list. You can just stare at this, absorb what's going on, and when you're done reading all the edges, you just output the lists. This is in pseudocode, so the output is going to be some function you make, but yeah. I've made the constraint small so you can also test out an adjacency matrix for this, but again, it's not going to be nearly as useful as the adjacency list, so you should use the adjacency list. Okay, now you'll probably notice that problem was really basic. Is that really the best we can do? And the answer is, with your current knowledge, pretty much. Again, you basically only have definitions. There's not much you can do without knowing more algorithms for processing graphs, apart from like discrete math proof stuff, which is not competitive programming, really. So let's learn these algorithms. There are two that I'm going to cover, and both of these ultimately do the same thing. They require you to pick some starting node or some target node, and they'll visit all the nodes that are connected to or reachable from, depending on if it's directed or not, that target node. But these algorithms work in different ways, and both of them are pretty worth learning because one of them is more powerful and the other is more simple to code. And also, like, there are some algorithms where you need a specific one, and yeah, so it's worth learning both of them. Let's start with the more powerful one because this does not require recursion, so we're still in the territory of no prerequisites. Again, the point of this is to pick a target node and visit all the nodes that are reachable from that target node, or in the undirected case, all the nodes that are connected. So here's the gist. First, we visit all nodes that are distance 0 from the target node, which is just the target node itself. There's no other node that's distance 0. Then we visit all nodes at distance 1. Then we visit all nodes at distance 2. Then we visit all nodes at distance 3, etc. Until there are no nodes left to visit. And that's it. That's BFS. Distance in this context means the shortest possible distance. So if there are multiple paths from the target to some node, the distance would be based on the shortest path. This is called breadth first search, or BFS, and it's called this because we visit all the nodes at a certain distance at the same time, so you can kind of visualize it as expanding wide. It doesn't make the most sense in graphs, honestly, and honestly it's not the best name, but it makes more sense when I compare it to the other algorithm. So if you're confused on why it's called BFS, just wait until then. It'll probably make more sense. So let's figure out how we can implement this. I'm going to ask a bunch of questions, and I recommend you pause the video for each one, because it's better if you invent the parts of the algorithm yourself instead of just me telling you each one. That way it'll be more intuitive, you'll get a better understanding of it. So first I ask, how do we find all the nodes at distance 1? Pause and think. And the answer is, these are just the neighbors of the target node A, right? Like that's it. Distance 1, neighbors of A. That's all it can be. If something is not a neighbor of A, then it can't possibly be distance 1. So now, how about distance 2? Pause and think. Well, these are just the neighbors of the nodes at distance 1. But this set of neighbors includes the target node. We don't want to check the target node again because we've already done that. If we check it again, then we'll get stuck in an infinite loop and we'll just keep checking the same nodes over and over. Like we'll check A, then B, then A, then B, then A, then B, right? It doesn't make sense. So, how can we avoid visiting a node more than once? Pause and think. So the classic way to do this is to store an array that tells us if we've already visited a node or not. And if we did already visit a node, we just don't do it again. And when we visit a node, we mark that we visited it. And to get distance 3 and in general distance x, we can just use the neighbors of nodes at distance 2 or x minus 1, because to get to a node at distance x minus 1, to get from a node at distance x minus 1 to distance x, we take one edge, so the distance should be 1 greater because it's 1 away, like if it's a neighbor. So yeah, for higher distances, we do the same thing. Okay, so that's how we implement BFS. But like code? How? The easiest way to do this is to use a special data structure called a queue. So let's go over how a queue works. It's basically identical to a queue in real life. Let's imagine a line of people waiting for, say, food at a restaurant. When someone orders, they leave the front of the line. And when someone enters, they hopefully enter at the back of the line. And in the context of this problem, why is a queue useful? Because this will allow us to process a node than its neighbors. We start by adding the target node to the queue. Then we continuously process the node at the front of the queue. And when we process a node, we add its neighbors to the back of the queue. Then we remove that node from the front of the queue, the node that we're currently processing. Do you see how doing this will process nodes in order of distance? When processing the target node, all its neighbors, the nodes of distance 1, in this case the blue ones, are added to the queue. Then when we process the nodes of distance 1, we'll process all the nodes of distance 1 together because they were all added to the queue together. And all the nodes of distance 2 will be added to the back of the queue. And so we'll process the nodes of distance 2 only when we're done with processing the nodes of distance 1, because that's how the queue works. And for the distance 3 nodes, we do the same thing. We process them only after we're done with distance 2. And this continues on until we process all the nodes. So I'll show the code here, and then we'll do a full dry run of the graph. So in pseudocode, here's how we do this. We start by pushing the target node to the queue, then we process the nodes in the queue by adding the nodes and neighbors to the back of the queue. We also make sure to not add the same node to the queue twice. Yeah, so instead of not visiting the same node twice, we do this extra optimization where we don't put a node in the queue more than once. So in this case, instead of a visited array, we would have an array representing in queue, where a node is in the queue, or when we put a node in the queue, we mark it as in the queue, and then we never put a node in the queue more than once. So this saves memory as well as time, because now instead of the possible memory being the number of edges, which could be the total number of entries in the queue, it's simply the number of vertices. You can spend some time thinking about why it optimizes memory like that, but yeah, it does. So now let's do a full dry run of this graph. I think this slide speaks for itself. There's not really much I can commentate on it, so just pause and process it. And use this to confirm your understanding of how the algorithm works. You don't have to memorize it. You just have to just make sure whatever you're thinking about BFS, make sure that this corroborates with it. Make sure that this makes sense in your head. So the time complexity of this is OV plus E, since each vertex is processed in the queue at most once, and each edge is considered at most twice, one for each vertex that it's attached to. And the space complexity is O of V, since each node is put in the queue at most once. Feel free to do some dry runs of other graphs to get a better feel for the algorithm, but this previous one should be roughly sufficient. And there's one other thing that's worth mentioning. Is this algorithm actually correct? Like, are the shortest distances really going to be correct? When we visit a node at distance 3, for example, can we be completely sure that it's not actually distance 2, for example? And the answer is yes. Let me prove why. Imagine we get a distance wrong. Like, let's say we say the distance for C is 3 when it's actually 2. Now, if its correct distance is 2, then that means it's adjacent to a node of distance 1. Let's say that node is B. If we said C's distance is 3, then we must have gotten B's distance wrong too, because otherwise we would have visited C after visiting B, and therefore we would have marked C's distance as 2 since B's distance is 1. So we must have marked B's distance as 2 while it's actually 1. But B, being at actual distance 1, is adjacent to the target node, A. And there's no way we got A's distance wrong. Like, the algorithm would just not do that. We put A in the queue first. It has to be distance 0. So the algorithm can't have actually gotten B's distance wrong because it didn't get A's distance wrong. And therefore the algorithm can't have gotten C's distance wrong because it didn't get B's distance wrong. So this is kind of a proof by contradiction. And this proof works for any node. If we get a node's distance wrong, then we can trace its shortest path back to the target node A, which we did here, and prove that we in fact could not have gotten that node's distance wrong. The algorithm just would not be wrong there. The way to formalize this proof is with induction. You can kind of see how it works here. I don't really care enough to do that proof here, but you can feel free to try if you want. It's induction on the distance, I think. Yeah. Anyway, on to the other algorithm. This one is probably simpler to understand, but at the same time, you need to know recursion for it. You have to absolutely understand recursion. So go learn that if you don't know it. You can check the description for a resource on it. Now this accomplishes the same thing as BFS, where it finds all the nodes that are reachable from a target node, but it does so in a different way. The concept is actually really simple, probably simpler than BFS, but you do need recursion, so maybe it's not so easy. But anyway, let's visit the target node. Then we recursively visit all the neighbors of the target node. Then we recursively visit the neighbors of those nodes as well. And we recursively visit the neighbors of whatever node we're currently visiting. We do this until all nodes are visited. So in some ways, in terms of comparing it to BFS, for DFS, because recursion works with a stack, we use a stack to add the neighbors to, and then we process the nodes in order of the stack. But in terms of BFS, we process the nodes with a queue. So it's sort of similar, but it's also sort of different. But yeah, once again, we can't visit nodes that are already visited, or we'll run into an infinite loop. So this is what the code would look like. Again, we're implicitly using a recursive stack for this instead of a queue. So it's not actually that different from BFS, but it's simpler to code because recursion is very light. So when we visit a node, we mark it as visited, then we recursively visit each of its neighbors. This also makes a lot of sense to use an adjacency list for, since it directly gives us a list of each node's neighbors. So the time complexity is also O of v plus e, since each vertex and edge is considered O of 1 times. The space complexity is O of v, since the worst case is having all vertices on the recursive stack at the same time. Now, when using this algorithm, make sure that the online judge you're submitting to gives you enough stack space to handle the algorithm, because sometimes it doesn't. For example, Python could have some issues. I know C++ has had some issues sometimes. You might have to set the stack space yourself. I'm not sure. You would have to check that out for yourself. Now, this is called depth first search, or just DFS, because compared to BFS, it won't visit all nodes at distance 1 and then distance 2, etc. It won't necessarily do that. It prefers to kind of go deep and will visit nodes of various distances, because instead of processing all its neighbors simultaneously like BFS, it processes the entirety of one neighbor and the entirety of one of its neighbors, etc., before moving on to the next neighbor. So it will quickly venture deep into the graph instead of staying close to the target node. Now, this algorithm works for, say, visiting all nodes in a component, but it doesn't work for finding shortest distances. And I encourage you to try and figure out why yourself. Like, actually pause the video and try and figure out an edge case that breaks DFS for finding shortest distances. Okay, here's one if you didn't come up with one. Hopefully you did, because it's pretty simple. Since we don't decide on any particular order to visit neighbors in, for this graph, if A is the target node, we might immediately visit either B or C. But if we visit B first, then we'll say that the distance to C is 2, because we go A, B, C, which is obviously wrong. The distance to C should be 1 because it's adjacent to A. And if we visit C first, then we'll get the distance for B wrong. So no matter what, DFS will always be wrong on this graph. And the proof that we use for BFS doesn't work because of this exact edge case and other edge cases like this. Even if some node like C is adjacent to A, we may not have used this path, the path A to C, to set the distance to C. If we found C through a longer path, such as A, B, C, then we would get a longer distance. So the proof just doesn't apply to DFS, because being adjacent to A does not guarantee that we'll set the distance to 1. So now that we've got the basic graph search algorithms down, let's do some more problems. Knowing these algorithms is enough for a huge portion of graph problems, so you'll be pretty set for a while. And this first problem is fairly simple. It's just to give you a bit of practice with the search algorithms. You're given a connected, undirected graph, a start node S and an end node E. I'm just reading off the slide. Find and output the vertices on any path between S and E. Pause and try this. You can code it with the link in the description. You can submit it there. Now, there are a lot of ways to solve this problem, but I'll give a method that'll also be useful for other problems later on. Let's use DFS with S as the target node, or E if you want to be smart, but instead of just visiting a node, we'll also store the node we came from, which we'll call the parent of this node. So the node we were just at before visiting the current node. And that way, once we get to E, we can backtrack using the parents and find out how we got here from S. For example, here, when we go from B to A to get to D, we'll store that we came from A. And to get to A, we store that we came from B, so we can backtrack through from D to B and get the path. We can also do this with BFS, and this trick of storing parents will be useful for many more problems, but DFS is pretty simple. The code isn't that different here for normal DFS. We just add this extra bit of information about parents. We also have to reverse the path here when we backtrack because we went from E to S. Unless you start the DFS from the end, then you have to reverse the path because we backtrack from the end to the start and we get the path backwards. Okay, problem 2, or 3 if you're counting. You're given an undirected graph, and your task is to output the nodes in each connected components. This is just a basic skill test, and being able to do this is essential for tons of graph problems, so pause and implement this. Low battery, that's fun. If you're stuck, here's how we do it. We run a DFS or BFS from every node and record the nodes we encounter in each search. But there's a problem here. If we run a DFS from every node, then that could be a problem for time complexity. And plus, we would visit each component multiple times since we start the DFS from every node. For example, if we DFS from B and G, then we would record that component twice. So let's use our visited array to our advantage. By definition, DFS will visit every node in the component. So when we visit a component, every node in that component will be marked as visited. So if we encounter a node that's been visited, then that tells us that we already checked that whole component. So we don't need to do it again. So instead of DFSing from every node, let's just DFS to every node that wasn't visited by a previous DFS. That way, every node and every component is processed exactly once. Here's what the code looks like for this. Should be pretty intuitive. We just DFS from every node that's not visited. Okay, this next problem should be pretty obvious given how I've structured this lesson, but this is also essential to be able to code. These past 3 problems are really just basic skill tests. Can you code BFS? Can you code DFS? So I will include this as a test anyway. If you want harder problems, check out the link in the description, and then scroll down to the bottom. Here you're given an unweighted, undirected graph and a source node S. Your task is to find the length of the shortest path from S to every other node. If a node is not reachable from S, we mark its distance as -1. Pause and try it. Hopefully you're paying attention earlier because this is exactly what BFS does for you. We prove this whole thing. So this is just, can you code BFS? So here, run BFS, but also store in the queue the distance of each node to S. Then for any neighbor, the distance is the distance of your current node plus 1 because it's 1 away from the current node. So this is what the code looks like. It's very similar to normal BFS, but we just add in the extra information of the distance to each node. In this case, we can create a class or a structure called node, and that node will store the index of the node and the distance itself. And then note that every time we push a new node, we add 1 to its distance because it's 1 away from our current node. Okay, this last problem is one that you may not be immediately prepared for. It's going to be significantly harder than the last 3 problems, so you should feel accomplished if you get it, is what I'm saying. So you're given a directed graph, and your task is to find out if there's a cycle in it. Again, directed graph. This also works for undirected, but directed is harder, so I want to challenge you. If so, output the nodes of any cycle. So pause and try it. Okay, first, what are our tools? We only have DFS and BFS. It turns out that this is tough to do with BFS, so let's try DFS and see where it takes us. So yeah, in your thought process, you would try BFS, you would get nowhere with it, and you would eventually rule it out. So eventually you have to try DFS. So during our DFS, how do we know if we found a cycle? Pause and think if you want. A good guess is we have a cycle if we hit a node we already visited. And that sounds good, right? Because if we already visited a node, then we must have gone through a cycle to go from that node and then get back to that node, right? Well, the answer is no, because consider this case to the right. We visit node B, then we finish with node B, go back up to node A in the DFS, and then visit C and encounter B again. We visited B before, and we encounter B again, but this is obviously not a cycle. But sometimes checking visited nodes does work, because consider this case. We visit A, then B, then C, then B again, and B, C, B is a cycle. It may look weird, but this is a valid cycle because it uses the edges and starts and ends at the same node. So the thing is, there's a difference between these two Bs. In the first case, which is on the left, we visit B, then we are completely done with B when we encounter B a second time. We process B, go back to A, then find B a second time. But in the second case, we're still processing B when we encounter it again. We never left B and went back up to A. Considering the code for processing B, we would be in the middle of this loop. We would be in the middle of visiting the neighbors of B. So the main difference between these two cases can be illustrated by looking at how DFS works. Both times we start at A, but at any given moment we've processed the path from A to whatever node we're currently at. In the second example, this path is A to B to C to B. You can see there's an obvious cycle here, because we encounter B again when we're still in the middle of processing B. So in searching for a cycle that starts at B, we found B again, meaning we started from B and ending up back at B, making a cycle. In the first example, this path is A to C to B because we already exited B before encountering again. So you can see clearly there is no cycle in A to C to B. This path can also be considered the recursive stack that we create when we run DFS. But regardless of how we think about it, we need some way to distinguish whether some node is currently on the stack or if we're already completely done with that node. So instead of just visited and unvisited, let's add a new state. We will have three states. We'll have unvisited, processing, and exited. Unvisited is self-explanatory. Processing means we're still processing that node. We're still in the middle of recursively processing one of its neighbors. And exited means we've gone through all the neighbors of that node and we've concluded that there's no cycle that starts or is reachable from that node. So this distinguishes our two cases. In the first case, or the left, the state of B is exited, meaning it doesn't work as a cycle. In the second, the state of B is processing means we found B while B is already on a recursive stack, so we found a cycle. So the way this works is, if some node is exited, it's not a cycle. If some node is processing, then it is a cycle. Okay, two questions remain. The first is, does this actually work? Is there a possibility that we don't find a cycle with this algorithm? Will this algorithm work? The answer is yes. We will not miss any cycle as long as it's reachable from our starting node. And here's a quick explanation of why. Imagine we start at A and eventually we get to B. So if some cycle is reachable from our starting node, then all of its nodes are also reachable. So eventually we'll be processing B. Now consider this graphic that represents the cycle. Since Z is reachable from B, it may take a long time to get to Z from B, but Z must eventually be reachable from B. Eventually we have to arrive at Z because we're processing B and then we have to arrive at Z. Or maybe we find Z through A and we find Z before we reach B, but then we'll get the cycle to Z. So since Z is reachable from B, eventually we must arrive at Z. Then since Z has an edge to B, we'll find a cycle since we end up back at B while it's in its processing phase. We went from B through some sequence of nodes to Z, and then eventually we go back to B. Now it's important to note that we may not find this exact cycle. All that's guaranteed is that Z is reachable from B. So we might find some other cycle that goes through B and Z. But we're going to find some cycle, since the existence of the cycle implies that Z has to be reachable from B. The cycle just means that Z is reachable from B. So if there's a cycle reachable from B, then we're guaranteed to find some cycle reachable from B, or some cycle through B. It's not necessarily this exact cycle that we're looking at, but it's going to be some cycle, because Z is reachable from B. That is guaranteed. So the other question is, do we have to repeat this DFS for every node and reset the state array every time? The answer for this is no, because if we mark a node as exited, then it means we looked at every node that it can reach by the nature of DFS. If there was a cycle among the nodes that it could reach, then we would have found it, because by the proof earlier, we will find a cycle if a cycle is reachable. But we didn't find any cycle reachable from B. So we can conclude that no cycle is reachable from B. And no cycle is reachable from any exited node because we already looked at all of the possibilities for cycles. So that means that there's no point visiting an exited node again because we know we won't find a cycle if we reach it. So each node is processed at most once, and its state will go from unvisited to processing and finally to exited when we're done with it. But we still do have to try DFS from every node, because if we only do it from one node, what happens if there are multiple components, or some nodes aren't reachable from that single starting node? Then we won't find the cycle. So we have to DFS from every node, but we don't have to check exited nodes ever again. So our main loop, similar to component finding, will attempt to DFS from every node that hasn't already been exited. That means our time complexity is O of v plus e, since each node and edge is processed O of 1 times. Here's the code. On this slide, it's kind of ugly. You probably want to check out the website for it. Again, it's in the description. But the code just represents this whole algorithm, where we mark a node as processing when we enter it and exited when we're done with it. To get the cycle's nodes, we can keep track of the recursive stack of nodes and use that stack to figure out the cycle when we find it. When we find that cycle, we go back up through the stack to the node that we found the cycle on, and then we get all the nodes in order based on their order in the stack. You should probably spend some time and think about this yourself. You can think about how you would code this, and then think about this solution if you can't figure it out yourself. And then it should make sense if you give it some thought for how we recover the cycle itself. There are many other ways to get the nodes in the cycle. This is just one of them, but this is the simplest way I could think of, so yeah. And yeah, that's about it. These problems, except for cycle detection maybe, were pretty basic because they're just intended to be an introduction. There are basic skill tests, make sure you can code certain things. So if you want more problems, harder problems, more diverse problems, less standard problems, check out the description for the website. I've said that so many times now, where I'll link my past video on graph theory, why did I say it like that? Graph theory, and a place where you can find a bunch more problems, namely Codeforce's other sites as well. That's all. Goodbye.